So yeah, it's a pleasure to talk to everyone at this conference. Of course, it would have been lovely to be in Beverly Hills and in Los Angeles during this time of year, maybe for a future time. Okay, so today I'm going to talk about work that I did with Li Gao this summer. It was here in the audience. This was when he was at Texas A&M, and now he's in Munich. And it's about this topic of recoverability that kind of became a hot topic to entropy fans everywhere. Okay, good. So yes, we've talked, we're obsessed with relative entropy. This is its definition. And I think you'll have all seen this many times now. It has a data processing inequality. So this is really just to establish notation. Throughout, rho and sigma will be states, and phi will be a quantum channel, completely positive trace preserving map. Okay, so there were a number of refinements of the data processing inequality. This is one that we worked on as a group. I guess it's 5 years ago now. Some of these co-authors are here in the audience also. So this gives a physically meaningful refinement of the data processing inequality for quantum relative entropy. And here the term that we have is a negative log fidelity, where I'm defining fidelity this way, like Holvan and Richard Joseph did in their papers. So the strongest result that we had in this paper was of this form, where we have an average negative log fidelity with respect to a probability measure that I won't define, but it kind of looks like a bell curve, but it has fatter tails than a bell curve. And this expresses, so if this upper bound is small, then it means that you can recover rho well from the noisy version of rho by applying what's called rotated Petz map. Okay, so there's kind of a lot of notation if you haven't seen this stuff before, but it's been appeared in some of the earlier talks. So this right here is what's called Petz recovery map, and it's expressed in terms of the noisy version of sigma, and the channel adjoint. And this is a quantum analog of the Bayes inversion map from the classical Bayes theorem. So that's an interesting way to think about it. And to prove this inequality, we needed to include these rotations, these unitary rotations. Okay, so then with that, using the concavity of negative log and fidelity, you can bring this average inside, and then you get what's called universal Petz recovery map. So why is it called universal? The lower bound, this map only depends on the sigma state and the noisy channel, and there's no prefactor that depends on rho. So it finds use in quantum error correction, and indeed, people working in high energy physics have used this. And then if you linearize the logarithm and use known relations between fidelity and trace distance, you can express the lower bound in terms of the trace distance. Okay, so that's some known results. And in this talk, we're looking to refine this kind of statement. And another, this was a very nice result that came a bit later, but due to Carlen and Vershynina, who are both present in this workshop. So the lower bound features the Petz recovery map itself. So up here, we needed these rotations. It's a bit more complicated with this integral, and they were able to establish this lower bound with the original Petz recovery map. But this is one of their the statement I'm showing here is recovering the sigma state with respect to the Petz map for rho. And when they do this, they get a prefactor related to the relative modular operator. What I'm not showing also in their paper, they show how to flip this around to get a statement in terms of recovering rho from the sigma Petz recovery map. So they get that statement as well. But there's this prefactor that depends on the state rho. So maybe some further work could improve that. Okay, so that was some starting point for our work, which I'm going to get to eventually. And let's talk about more general divergences. So already we've seen some, I think in earlier, I think from Anna's talk, we saw f-divergences. So I'll just define this again for you. We take the relative modular operator and a function, and we need it to be operator monotone decreasing. You can define it for an arbitrary function, but it's only useful if the function is operator monotone decreasing. So you apply the function to the relative modular operator, then evaluate this trace. And there's a way that you can vectorize this by expressing the square root of the density matrix as a vector. Some interesting special cases to connect back to cases of physical interest are when you take f to be the negative logarithm, you get back to relative entropy. If you take it to be the power function, then you get Rényi quasi-relative entropies. And this parameter S it's different from alpha, so that's why we call it S. And this choice is giving you either a operator convex or operator concave function. Okay, both of those are useful. And then you can construct the Petz-Rényi relative entropy as we've seen from this quasi-entropy. I should mention that all of this theory, Petz was inspired by his colleague Imre Cezar, both at the Rényi Institute in Hungary. Many years earlier, I believe in the late 60s or early 70s, I forget the exact date, Cezar and others worked on classical f-divergences. And so Petz was interested in the non-commutative generalization of that concept. Okay, so in Petz's work, he established the data processing inequality if f is an operator monotone decreasing function. And then more recently, we saw this very nice refinement of the data processing inequality in terms of recoverability, right? So here again, using the rho Petz recovery to recover the sigma state. And I believe in this paper, they also had ways to flip it around to talk about recovering the rho state from using the sigma Petz recovery map. And K is some constant that depends on the relative modular operator and the parameter S. Okay, so this is some prior work of interest. Another divergence that comes up in applications is the sandwiched Rényi relative entropy. Omar was talking about that in his talk for a little bit. And we again use the sandwiched Rényi quasi-entropy to define it. And this has also been extended to general von Neumann algebras by Mario Berta, who's here, his colleagues, and in an independent work by Anna Yankova. Okay, so after that happened, there was this lingering question: how can we express quantities like sandwiched Rényi as an f-divergence? And so I wrote this paper about that, and I called it optimized f-divergence. And so it's very similar to what we had for Petz's f-divergence, except this rho you instead allow it to be a state that you optimize over, okay? So you do that and you get this optimized f-divergence, and you also want f to be operator monotone decreasing. So why is that useful? Well, I don't know, many times while sitting in math conferences and reading math papers, there's like the battle for the simplest proof, and I'll get to that eventually. By doing this, you get a very nice proof, very simple proof of data processing for these optimized f-divergences that's in the exact same spirit as Petz's original proof of data processing for the unoptimized f-divergence. So we'll get to that in a few slides. Okay, so if you pick f to be negative log, you again get the Umagaki relative entropy, the standard quantum relative entropy. If you pick it to be a power function, then you get the sandwiched Rényi with this alternate parameterization. Okay, and yes, then we can re-express the sandwich Rényi in terms of this alpha prime, which is the Holder conjugate of alpha, the alpha parameter that we usually have for sandwich Rényi relative entropy. Okay, and for this optimized f-divergence, we also have a data processing inequality. So let's quickly talk about how that works. I think it was in Anna's talk. Yes, we saw that when we're trying to prove data processing, it suffices to consider the case of partial trace. So we'll do that here. We'll take the channel to be the partial trace, and we'll define this isometry from linear operators in the smaller space to the larger space like this, okay? And then when you plug in the marginal of the row state, you'll get out, if you plug in the square root of the marginal, you get the square root of the global state. And then a key observation that you can make, it's just a calculation, you write it out, is if we pick this state here to be the omega, some arbitrary omega state, and we apply the row Petz recovery, then we'll get, and we plug in the global sigma state, we'll get the marginal sigma state. The Petz recovery will sort of cancel out, and we'll be left with this omega state that we plugged in for the B system. So that's an important observation. And then once you have all these ingredients, you get data processing in a few lines. So we'll just show that real quickly. So the way this works is use the definition of optimized f-divergence. So we're optimizing over omega. Now we're using the observation from the previous slide. We're substituting this relative modular operator on the smaller systems to with this equality that we have here. Okay. Now, since this is an isometry, and this is operator monotone decreasing, we can apply operator Jensen inequality. So that's really the core step. You apply operator Jensen, and then this is just some state on the global system, right? This is applying the Petz recovery map to the omega B state, and then it gives you some global states. And then if you optimize over all states, you get something larger, and that's the optimized f-divergence. So that's it. That's the data processing in a few lines. And that was essentially the story of this earlier paper. And if you examine Petz's proof of data processing, it's essentially the same proof. And when you use sandwiched Rényi, you get the data processing for the full range of alpha for which it's known to hold, which is 1/2 to infinity. Okay, so in this work, this is the kind of thing we're trying to refine. So let's start getting to the results. I think I have about 7 minutes left. So in the joint work with Li Gao, we have a number of results. I'm just going to highlight a few of them. So one of them is this data processing, refinement of data processing, and it improves on the Carlen and Vershynina data processing refinement because we have this. This is the prefactor instead of the relative modular operator. And then we know that this order 2 quasi-Rényi relative entropy is less than the operator norm of the relative modular operator, which is what appeared in their work. And yes, this is also about recovering sigma from the row state. Okay. And then one thing we did is that we incorporated T can be an arbitrary real number. So if you plug in T equals 0, you get back a statement for the Petz recovery, but then we also have statements for any rotated Petz recovery map as well. And so that was some statement that we hadn't quite seen before in the literature, where you could plug in an arbitrary T. Okay, all that was there before was like if there was a supremum over T, or if you took an average over T. Okay, and then something that's an advantage of this over the bound of Carlen and Vershynina is that we can plug in states of experimental interest. You know, if you start looking into the experimental literature on quantum information, a recurring theme is these bosonic Gaussian states, because they can be prepared easily in the lab. And this quantity can be finite for some bosonic Gaussian states. There are conditions under which this will be finite depending on the covariance matrices of the states. While this operator norm will be infinite, you know, for Gaussian states that are faithful. Okay, so that was one result. Another result is about recovering the row state in terms by using the sigma Petz recovery map. And now we have a different prefactor, and it's kind of like, you know, here we had, you know, to get from this first result to the second result, it's kind of like you're flipping rho and sigma, but you know, the details are different with how it works out, but on like a superficial level, you see that we're just like, this constant comes about by flipping rho and sigma. But the constant, it's now a function of this in a parameter epsilon that you can tune, where epsilon's an arbitrary, strictly positive number. And then again, we have the remainder term is expressed in terms of rotated Petz recovery maps. So you can choose T how you please. Okay, good. And another statement we can make is a recovery statement for sandwiched quasi-relative entropy. So this is, this had not appeared in the literature before. You know, we talked about Anna and Eric Carlin's work on quasi-Rényi relative entropies. So now we can use the sandwiched quasi-1 and get lower bounds. And, you know, lower bounds kind of similar, but there's a different exponent here and a different constant. Now the constant involves the max relative entropy. Okay, so we also get improvements for the quasi-Rényi relative entropy, the unoptimized one. And then, you know, these results we've extended to general von Neumann algebras in a very general setting, this type 3 setting. There's an open question about, could we have the universal Petz recovery map here? We didn't quite know how to do that, so that's still open. I have like 2 minutes. I just wanted to give you a taste of the proof. I'll do my best. So let's make this shorthand. Delta will be this relative modular operator in the larger space with the optimal choice of this marginal state for the optimized f-divergence, and this will be the relative modular operator on the smaller space. So we use an integral representation. I should mention what we're doing. It's very much inspired by the paper of Eric and Anna, and but we have some departures in the details, but conceptually we're using similar ideas. Okay, so we use this integral representation to get a lower bound on the difference of optimized f-divergences like this, and then you do some rewriting, and you can write this the lower bound like this. So now the question is to link these UL vectors to this difference of optimized f-divergences. Okay, so then let's define these UT vectors. So it depends on these U lambdas, okay? And this was a clever integral representation that Li, was aware of. And so that plays a role in the proof. And this inequality, which we were aware of from Eric and Anna's work. And okay, skipping a lot of details, we use this inequality to go from matrices to vectors, and some algebraic manipulations with this integral representation to get this upper bound on the recovered version of rho. I think I mean to have a partial, the marginal state here. Sorry about that typo. Okay, and so this step links the UL vectors to this UT vector, which is used as an upper bound on the recovery error. Okay, and then what you do is now we have to analyze this upper bound term. So you split it into three. You split the integral for UT into three different intervals. So this is, following our Eric and Anna again, apply the triangle inequality, and then various tricks to bound the three different terms like this. So this is kind of like a meta bound that you can plug into. You can make particular choices of the optimized f-divergence, such as negative logs, such as the power functions. Maybe there will be other interesting functions you could look at, but those are the ones we studied. So you plug in those, you optimize this S and T parameter, and then you get the claimed statements that I made. Okay, so I think I'll just stop here, and you can read these. Thanks for your time.